Hi everyone. In this video we're going to be looking at how we can solve exponential equations and we're going to be doing it without logarithms because we haven't learnt that yet. So there's some equations that can be solved pretty straightforwardly without the use of logs, and that's what we're going to look at here. Okay, so just to begin with, we're going to look at this rule that's going to help you in the process of solving these. Okay, and that is if a to the power of x equals a to the power of y, then it must be that x is equal to y. Okay, a is some base of some kind, and x and y are the indices of that base. Now, we've got these two dot points here, okay, and this is like your guidelines, I guess you can say, of how to solve exponential equations. And there's really two types of exponential equations that you'll encounter. One is fairly straightforward, where all you have to do is apply this rule that we've written here. The other one's a little bit more involved, and that requires you using a substitution and turning it into a quadratic equation, which we'll see an example of later on. Okay, so you need to get good at recognizing the difference between the two classes of questions and being able to apply the correct method to solve whichever class it is. Okay, so we'll look at just first three examples where we're going to be using this rule to solve those equations. Then example 4, we'll look at one where you have to turn it into a quadratic. Okay, so example number 1, we've got 4 to the power of x equals 256. All right, so normally what you want to try and do is express all your terms with the same base. Okay, now it can be done in this case. We can turn 256 into a power of 4, because 256 is equal to 4 to the power of 4. Okay, 4 times 4 times 4 times 4 is 256. So I've just rewritten 256 as 4 to the power of 4, and now we can apply our rule from before. Remember, we said if a to the power of x is equal to a to the power of y, then it must be that x equals y. And that's exactly what we've got here. Okay, we've got 4 to the power of x equals 4 to the power of 4, so it must be that x equals 4. Okay, those two powers must be equal to each other. All right, there we go, fairly straightforward. It can also be done changing these two bases into powers of 2. It's kind of unnecessary because 256 can be written as a power of 4, but we can do it anyway. So 4 to the power of x can be written as 2 squared to the power of x, and 256 can be written as 2 to the power of 8. Okay, using an index law, we can combine these two powers on the left here and write it as 2 to the power of 2x equals 2 to the power of 8, and so you get 2x equals 8 and x equals 4. So you end up with the same thing, it's just one or two more steps involved. Okay, moving on, example number 2. Again, we're going to apply our rule. At first we're going to express everything in the same base. So we can write 81 as 3 to the power of, well, what is it? 3 times 3 is 9, times 3 again, 27, times 3 again, 81. So we can write it as 3 to the power of 4. And we apply our rule. If we've got the same base on either side, and it must be that one power equals the other power. So we've got x minus 1 equals 4, and so we end up getting x equals 5. There we go. Okay, so that's all there is to it. Make sure you express all your terms in the same base, and then just equate exponents, equate the powers. Moving on to this one. Okay, slightly more involved, but not really. Again, first thing you should do, write everything in the same base. So we've got on the left 5 to the power of 2x minus 4 equals, and we can write 25 as 5 to the power of 2. So write it like this, 5 to the power of 2, and that's to the power of negative x plus 2. Using an index law, I can expand the right-hand side and turn that into 5 to the power of negative 2x plus 4. And at this point we can equate exponents, and we get 2x minus 4 equals negative 2x plus 4, and you solve it, you get 4x equals 8. and x equals 2. There we go. All right, so you can see this strategy we're employing here, write everything in the same base. Once it's all fixed up and you've used your index laws to expand everything, then you can just equate exponents. Okay, so example number 4, this is a different type of question. Okay, you need to be able to recognize that this is a different type of question. One major difference between this type of question and the ones we've just looked at is we are subtracting something or adding something. You could also do as well, right? If you see that happening, then most likely it's going to be this class of questions where we're going to have to do something different. Okay, so this type of question, I mean, it's a little bit non-obvious, but it is a quadratic in disguise. Okay, so let me show you how that works. I'm going to put everything onto one side. So I'm going to rewrite it as 9 to the power of x minus 12 times 3 to the power of x plus 27 equals 0. So I've just taken that onto the other side, and I've taken that onto the other side as well. Okay, now notice the 9 and the 3, okay, they're related to each other because 9 is 3 squared. 9 is a power of 3. So I can write the 9 as 3 squared to the power of x. All this stuff will just stay the same. But if you think about it, I can also write it as 3 to the power of x squared. Okay. If you don't believe me, use your index laws to expand these two and you'll end up with the same thing. Okay. So I'm going to write 9 to the power of x as 3 to the power of x squared. Okay. We've still got all this stuff here, minus 12 times 3 to the x plus 27 equals 0. So this should be reminding you of a quadratic now, okay? It might look a little bit different, but it is a quadratic in disguise. And the way that we can make it concrete is we can perform a substitution. So let's say that some other variable, call it u, we're going to replace, wherever we see 3 to the power of x, we're going to replace it with the letter u, okay? And so that's going to make this turn into u squared minus 12u plus 27 equals 0. There you go. That's a quadratic equation. And so what we can do now is employ whatever method you like to solve for u. You can use a quadratic equation. You can use a null factor theorem after factorizing, whatever you want. Solve for u. And then once you've solved for u, you can then re-substitute 3 to the power of x into that and then solve for x. Okay, so that's the general method of this class of question. So solving for u, I'm going to just factorize it. It's pretty easy to factorize. You get u minus 9 times u minus 3 equals 0. Okay, negative 9 times negative 3, positive 27, and negative 9 minus 3 is negative 12. And so from that we get u equals 9 and u equals 3 as two solutions to the quadratic. Now, we're not trying to solve for u, we're trying to solve for x. So we're going to re-substitute 3 to the power of x for u. You end up getting 3 to the x equals 9 and 3 to the x equals 3. And this becomes pretty easy to solve because we know 3 squared equals 9, so that means x equals 2 for that one. And we also know 3 to the power of 1 equals 3, so that means x equals 1 for that one. Okay, so there's two solutions to this problem. There you go. Okay, so that's how we do this kind of question. Okay, turn it into a quadratic by performing the substitution, solve the quadratic, and then re-substitute to solve for x. Cool. All right. Lastly, we're going to talk briefly about inequalities. For the most part, they are exactly the same as equations, and you employ the same methods to solve them. It's just we have to make sure that one thing in particular is true. Okay, and that's this. If we've got a to the power of x is greater than a to the power of y, and our base a is greater than 1, then we can say that x is greater than y. Okay, but that part here is really important. Your base has to be greater than 1. If it's not, then what's going to happen is this inequality sign flips around. Okay, so if we say that a is between 0 and 1, then we flip that around, okay? I prefer just turning your base into a number greater than 1 to begin with, okay? Then you don't have to worry about flipping around any signs anywhere, and that leaves you one less step to do at the end. Okay, so to do that, we use this rule here. Okay, if you've got 1 divided by something, then you can turn that into that something to the power of -1. Okay, just quickly, I'm going to show you how to do that for fractions that don't have a 1 in the numerator. So let's say, for example, we've got 2 over 3 to the power of x. Okay, so right now, that's an exponential with a base that's between 0 and 1. Okay, we don't want to have that when we're doing these inequalities. So how do we turn that into something that's greater than 1? Well, here's a little trick that you can do. If you've got something that looks like that, that is exactly the same as flipping that fraction upside down and then writing it as a negative exponent instead. Okay, so that's a little trick you can do, and it's basically just putting this into action. Right? If you go back the other way, so right now, what we've got on the right-hand side is 3 over 2 to the power of -x. We can write that as 1 over 3 over 2 to the power of x. Okay, so what we're doing here is we're doing 1 divided by a fraction, basically. If you're doing 1 divided by a fraction, you can turn it into a multiplication by flipping the fraction upside down and then multiplying it with the numerator. So you'll get 1 times, flipped upside down, 2 on 3. And that's how you get that back at the end. Okay, so that's a little trick you can do if you want to turn it into a base that's larger than 1. Let's see how we can use this with some examples. So 16 to the power of x is greater than 2. All right, same as before, write everything in the same base if you can, and also try and write them with bases that are larger than 1. So here I can write 16 as 2 to the power of 4 to the power of x greater than 2. Index law, I can write this as 2 to the power of 4x is greater than 2. Just know that that's to the power of 1 there. And so I can say, because my bases are greater than 1, that 4x is greater than 1. And solving for x, I get x is greater than 1 over 4. Okay? So exactly the same process as before, just with an inequality sign in there instead of an equal sign. Last question. All right, so again, same thing, write everything in the same base. So 1 over 16 can be written as 1 over 2 to the power of 4, because 16 is 2 to the power of 4. Now, right now, this is not a base that is greater than 1, it's a fraction. So what we can do is flip it upside down and write it with a negative index instead. And we can write it like this, 2 to the power of -4. There we go. So now our bases are both the same, they're both 2's, and they're both larger than 1. And so now what we can say is that -3x plus 1 is less than -4, and solve for x. -3x is less than -5, and x is greater than 5 on 3. Why is it greater than instead of less than now? Because we had to divide both sides by -3. So just be careful when you do that. All right, that's it. That's all I've got to say. See you next time.